monitor quantum systems. These are systems which are being measured. Now, a big advance in measured quantum systems which occurred over the last 5, maybe 7 years has to do with the fact that it's been realized that measurements can be used not only to learn or to probe quantum systems, but also to steer them to evolve in a particular way. And steering quantum systems by measurements provides an alternative path to quantum systems to evolve in time, an alternative to conventional quantum mechanics. And now it's been realized that by using measurements to steer quantum systems, we can make them do things which conventional Hamiltonian evolution doesn't seem to be able to do. And in particular, new quantum phases of matter were identified if matter evolves under the action of measurements. Now, we had very inspiring talk by David Hughes on Monday telling us about some of these phases. But I would like today to take a step back and think about it not just in terms of what kind of quantum phases you can get if you have measurements, but kind of think more generally. What does it even mean that a quantum system evolves under the action of measurements? We're so used to think of Hamiltonians and Hamiltonian evolution that measurements bring something which we're not typically thinking about. I would even say that any quantum mechanics textbook, would have the very first section talking about measurements, and then it says, let's forget about all of this and move on to study Hamiltonians and Schrodinger equations. But so to understand measurements, we really need to maybe go back to our quantum mechanics class and open that textbook again and try to think about what measurements are and what they do. So today, my goal is to try to just kind of look at measurements more generally and just to ask, how are they different from unitary evolution of wave functions? What do they do which conventional unitary evolution cannot do? So I started thinking about these issues only maybe about a year ago, in part because I couldn't fully understand what was happening in this field of phases of matter controlled by measurements. And I realized that, at least to me, I really needed to go back to basics in quantum mechanics. And so I'd like first to talk a little bit about very basic properties of measurements. And now I realize that some of you in this audience are expert on this, and I would apologize for talking about something so elementary, but I think it's worth talking about this since maybe not everybody is an expert, and also it's always good to review the basics. So let's first compare, well, let's first think about what measurements are. So we all know that wave functions evolve in time according to the Schrodinger equation, but they can also evolve by projective measurements, and that means a wave function gets acted on by some projection operator, and it changes abruptly from initial state to the final state given here. So we know this in principle, and now every measurement comes with its probability, and now we know that these P's are projection operators, which means they satisfy some properties, such as they sum to 1, and the square of a projection operator is equal to the projection operator. Now, this is a strange way of evolving wave functions, which we normally don't think about, because normally we think that wave function evolves according to this and not according to that. And it's worth maybe to think about what can we get from this new type of evolution. Not really new, but a type of evolution which has not been maybe taken seriously over the last 100 years and only started being seriously looked at recently. And so before I start talking about the effects of projective measurements on these wave functions, let's also note that there is an alternative way of doing measurements, which turns out to be very productive if you would like to evolve your wave function not abruptly by suddenly acting on it by projection operators, but more smoothly, more similar to Schrodinger equation. And so it's possible, instead of measuring the system itself, to couple it to some auxiliary degrees of freedom, which everybody likes to call ancilla. And so then if you couple your system to this ancilla and then evolve it with some unitary evolution operator, and then you measure the ancilla. So the result of the act of this unitary operator on this product takes you into some state which can be decomposed into the eigenstates of this ancilla. And then when you measure the ancilla, you project the ancilla onto one of its eigenstates, and that projects your system onto something given by these, where K is no longer a projection operator. It's more general than a projection operator, and the only constraint that K must satisfy from U being unitary is that sum should still add up to 1. And now K could be a projection operator in principle, but it could also be something else as long as this is satisfied. So such K operators are sometimes called quantum channels. Sometimes they're called Krauss operators. I don't know how the best name for them, but all I know is that we don't need to talk about projections necessarily. We can also think of these K operators. And now the great thing about K operators, they can be chosen to be close to identity. And then this evolution becomes infinitesimal for infinitesimal amounts of time. And then we can actually think of it as some kind of smooth evolution of the wave function. And that's how I would like to think about measurements today. Now, given this information, let's think about what we can learn about the system once we measured it. Given a state of the system, which we measured by acting by this K, we can evaluate maybe some observable. And so this is the expectation of this observable Q after the measurement has been carried out with the result M. So Km acted on my wave function. M is the outcome of that measurement. And then I measure the expectation of Q. So this Qm is an expectation of Q under the assumption or on the condition that a measurement has been done and the outcome was M. But maybe we might want to average then the result of this measurement over the, the result of measurement of Q over the all possible outcomes of the measurement M. And so to do that, I take this Q multiplied by the probability of the measurement, which very conveniently cancels its denominator, as many of those who started working in this field recently emphasize in their papers. You can see this discussed in many recent literature. And so the end result would be that the average of some quantum operator, quantum average, but also averaged over all the outcomes of these measurements, is given by the sum. And Km are these measurement Krauss operators, and Q are, Q is your physical observable. And so you could ask a question, what kind of expectation is this? And is it different from what we normally get when we compute expectations of quantum observables? And so one thing which we can notice that if Q commutes with K, then of course you can commute Q through K, and then you can use that completeness, that Km dagger, Km is 1, and just K completely drops out. So if Q commutes with K, then it doesn't even matter that you measured something in the past. And if you think about it, of course, it's kind of almost obvious, because if you measure something and then you measure Q, which is essentially the same as K, so in other words, you're kind of doing this measurement twice in some sense, and maybe it's not surprising that it doesn't even matter that you measured something in the past. But if Q doesn't commute with K, what kind of average is this? Is this similar to what you would have gotten without measurements, or is it differ, or does it differ in any way? And so you can restate the problem in the following way, defining the measured density matrix written here. This could be K dagger actually. We can calculate the expectation of Q as a trace over such sum density matrix, which is summed over all the outcomes of measurements. And we can discuss, is rho bar trivial in any sense, or is it non-trivial? Now, it's been argued in the literature that rho bar defined in this way is in some sense thermal. And so, in other words, these kind of averages after we've carried out measurements and then we averaged over the outcomes of these measurements, they kind of like, these measurements kind of thermalize the system. I don't really do anything else beyond this, but I found it very vague. I wanted to make a more precise statement about this rho bar. And it turns out that it's possible to make a statement that a rho bar can be produced by purely unitary evolution without any measurements. From that point of view, this rho bar is kind of trivial. In other words, you don't need to use measurements or to invoke measurements to produce this kind of measurement averaged rho bar. Okay, and I'll tell you, hopefully I'll be able to tell you why rho bar is the outcome, well, can be thought of as an outcome of a purely unitary evolution without measurements. But okay, given this information that calculating averages over, over states of the system averaged over outcomes of measurements, this kind of calculation in some sense is not particularly deep. You can even avoid invoking measurements altogether. We could still ask a question, what's then non-trivial about measurements? What is it about measurements which cannot be obtained purely by unitary evolution? And it turns out, it has been identified over the last 7 years, what we're supposed to look at is nonlinear observables, and somehow it becomes a key theme in this subject. So nonlinear observables are the ones such as the one defined here. So if QM, again, is the expectation of a quantum operator conditioned on the outcome of measurement M, we take something nonlinear, maybe just a square of this expectation of the quantum operator multiplied by probability and sum of all measurement outcomes. And if you plug in the algebra from the previous slide, you will see, of course, it's just square of that divided by this. In other words, it's this kind of ratio of traces. And this expression is nonlinear in the density matrix, and that's why it is called nonlinear observable. Now, this nonlinear observable can no longer be reduced in any sense to something which comes out of the evolution of a quantum system without any measurements. So once you start looking at nonlinear observables, that's when you start getting something new. And that's part of the reason why people look at things like entanglement entropy, because entanglement entropy is extremely nonlinear in terms of, if you express it in terms of the density matrix. Now, it is also possible, as you can convince yourself, to express nonlinear observables in terms of linear observables, but of a replicated system. You take your system, replicate it n times, write down this replicated density matrix, and with a little bit of work, you can convince yourself that nonlinear observables, such as this one, can be written as something linear in the replicated density matrix, but in the limit when the number of replicas is taken to 1. Now, you could ask, so if this nonlinear observable happens to be linear, but for the replicated system, does it mean that it's in some sense not non-trivial? Because linear observable should be trivial, and this nonlinear observable is linear, but for a replicated system. But of course, once you replicate system, you also make certain assumptions which are not valid physically, meaning that these measurements, they have to occur in every replica in a coordinated way. So you have to measure every replica and then demand that each replica gives you the same outcome of the measurement. That doesn't happen in real life if you physically replicate your system. And so that's why under these mathematical assumption not possible in real life, the linear observable gives you something which is in real life is a nonlinear observable. That's why this expression here is actually deeper than just something linear averaged over measurement outcomes. Okay, and now I also would like to ask one question here, which is, why do we need to take this replica limit n goes to 1? So that comes out of the algebra on the previous slide, but we also know that entanglement entropy can be calculated as n goes to 1 limit of these so-called Ranye entropies, and Ranye entropies themselves can be calculated in a replicated theory. So n goes to 1 limit corresponds to calculating von Neumann entropy as the limit of these Ranye entropies, but at the same time, it also corresponds to calculating nonlinear observables. And there has to be some connection between the two. And so far, I have not seen an explanation of that in the literature. We can have a discussion of this for quite a bit. So I'm not going to continue thinking about this issue. But I would like to ask this question. So how come that n goes to 1 limit occurs in two seemingly different settings? And is there any relationship? Those of you who studied problems with disorder, quench disorder, they know that typically we take the limit of replicas going to 0. Here, somehow, we have to take the limit of number of replicas goes to 1. And this is like a theme in this formalism. And there has to be some reason why replica limit n goes to 1 is important in these problems with measurements.
But Ranye entropies for finite also were part of it.
Yeah. So in other words, Ranye entropies for finite n are also interesting, you could say. So we don't need to look at von Neumann entropy as a matter of principle, but for these nonlinear observables, we do need to take the limit n goes to 1. But somehow that corresponds to von Neumann entropies. And is there any kind of relation for that? So that would be the question. Okay, and the last thing which I would like to bring up, which I have to bring up, even though I recognize that probably everybody here is familiar with this, nonlinear observables have this feature, which in the literature received the name of post-selection problem. And that is, so how would I go about measuring some quantum observable such as Q after I measured that quantity Km? So how would I do it in practice? Well, I would run my experiment. I would measure my Km with an outcome M, and then I would look at my observable Q and get some value Q. And I can call it QJM, where M labels the outcome of my measurement, and J labels different Qs, which I get conditioned on the previous outcome of that measurement. And so to calculate a linear observable, I just average these Qs over all possible, or all my runs. Every time I got different values of Q, I just average them all. But if I would like to calculate a nonlinear observable, I have to do something deeper. I have to collect all the outcomes of my experiment, giving me some values of Q for a given M. I have to calculate average over all Qs for a given M. Then I have to do something with this average, such as square it, for example, and then I have to average over all the outcomes of the measurements. And that is somehow fundamentally more complex process than here. In particular, if M has many different possible outcomes, and I could imagine that maybe M's is a set of measurements done across a large many-body system, and there are exponentially large number of possible M's I can get, and suddenly I have to generate enough data for each value of M out of exponentially large possible values of these M, and I have to assemble them together into this sum, and only then average over M. And maybe for very large systems, that is not even possible at all. And so there is still a question whether these kind of nonlinear observables can be actually seen in experiment on large systems on which I expect many different possible outcomes of measuring this M. And again, this has not been entirely answered. This question. Sometimes I think that some nonlinear observables, such as entanglement entropy, maybe it's possible to convert it into thermodynamic entropy and then just measure it by measuring heat capacity. But I'm not entirely sure if that's possible. And I know that some of you present here worked on this question and proposed various protocols of computing this type of averages, somehow avoiding this problem, which I just mentioned. But okay, this is all philosophical, and I'd like to move on. I'd like to just acknowledge that this problem exists, but also acknowledge that interesting new phenomena I expected in nonlinear observables. And somehow in linear observables, we don't expect to see anything new. Oh, and the last thing which I'd like to bring up, which is very speculative, but kind of interesting. So now that we're talking about measurements, we can ask a question which everybody for the last 100 years have been asking: at what point does the wave function actually collapse? If we look at the Schrodinger cat, and obviously we know in which state it is, but if a machine looks at the Schrodinger cat, does it know in what state it is, or does it just get entangled with it? Well, and so based on this idea of nonlinear measurements, we might say that as long as that machine has memory and can compare the results of previous measurements to results of later measurements, that machine is as good as any human at looking at the Schrodinger cat. Now, I don't know if that's what I just told you is enough to make this conclusion, but at least it's an interesting way of maybe improving our philosophical understanding of what measurements are based on just these arguments of nonlinear observables. All right, but now I'd like to move on. Everything which I said so far is sort of now well known, although maybe not appreciated by everyone. And I'd like to apply it to construct a functional integral describing a single quantum particle which is being measured. And part of the reason I'd like to do that is because it's very easy to sweep all the issues about the measurements under the rug by presenting a large quantum many-body system and start discussing its phases. But then I feel like that a big picture sometimes gets obscured by many details that you have to learn about if you're studying complex quantum many-body system. So why wouldn't we look at a single particle first? And now I imagine a particle which moves along a one-dimensional line, which is being measured. And now what does it mean that it's being measured? Well, let's say that I'm just trying to figure out if that particle is contained within some interval between A and B, and its wave function gets projected onto a wave function located or limited by this interval, and it's zero outside this interval. And so that's what it means to measure the particle and find it within this interval. It means to project its wave function by the action of this projection operator. Now, this kind of thing is very drastic because it takes your wave function and it changes it a lot. It nullifies it outside this interval. But I'd like to construct something which is more gentle, which allows the wave function to evolve continuously in time. And so instead of using this projection operator, I'll use this chaos operator, which can be written as exponential of some function v of x in such a way that if v is positive, it enhances that wave function at that point x, and if v is negative, it actually suppresses it. So I could imagine actually that v is 0 between a and b and minus infinity outside, and then this k becomes just this projection. But I can also take my v to be close to 0, and I actually multiply that by dt to emphasize that it's small. And then k is close to identity. Now, such k operator, you can also write it on the basis independent form with some function v of x. So it satisfies all the properties that we expect from such Krauss operators. So the outcomes of the measurements become the full function v of x. So given a function v of x, that's the result of my measurement. Since v of x kind of like, I mean, I can even choose v of x corresponding to projections to some intervals. In that case, that's the outcome of the measurement, that the particle is confined to that interval where v is not, in that case, minus infinity. But more generally, v of x labels different outcomes. So summation over m is integration over v, and it's very natural to say that v is a random Gaussian variable with some weight, which I call w, and that w has some width, and that width has to do with the width of the interval to which I confine my particle. And you can also show that this summation over m corresponds to averaging over v of k squared, and that is proportional to identity. And so it satisfies that completeness condition, this type of operator, so that this is the identity. Once you square k and average it over these v's, which corresponds to summation over the outcomes of measurements. Yeah, so the correct condition is it should be equal to the identity. Now, if you just literally do this calculation written here, you will get something which is proportional to the identity. Now you have the option. You can take this factor and just absorb it into your definition of k, take square root of it and just put it in k. Then it'll be identity. Or you can keep it here, but then you have to normalize your density matrix at the end of the calculation. It's whatever you prefer, but on a fundamental level, the best maybe is to take this factor and just insert it into k. And then this will be equal to the identity then. Okay, so let's see. And now, armed with these type of arguments, I can actually write down functional integral describing evolution of my particle, because exponential of v dt looks just like a potential in the Hamiltonian acting on my particle, except if I had a potential, there would have been minus I v dt, as we always have, because it's minus I Hamiltonian times dt. But now we don't have an I, and so we can write down the path integral where we have this v implementing our measurements, but with an I in front. So it's a non-unitary term in my Hamiltonian, or non-imaginary term in the path integral, which implements my measurements. And v should be thought of as a random function of both time and space if I'm measuring randomly in time and space with some average, well, which I'll encode by this function w. And so the conclusion here is that a randomly measured quantum system is described by a path integral with non-Hermitian random time-dependent terms, white noise in time. So they randomly change in time because different time slices correspond to different measurements and different measurement outcomes. And so that type of conclusion allows us to immediately start studying all sorts of things, starting from this particle. And so for such a simple problem of this particle, what I mean, if all I would like to do is to calculate linear observables, I will just set up a path integral. And the only subtlety is that I need to set up an integral for both psi and psi star, because I have to average psi star over the outcome of my measurements. In other words, density matrix, not just the wave function. And so I have to use Keldysh functional integral over path x plus and x minus, kind of moving forward and backward in time. And if I do that, that's what I get. Now, importantly, actually, the sign here is plus because these are non-Hermitian terms. And now I can average my density matrix over the outcome of measurements and generate this expression with this w, which is a correlation function of v's. Now, if I calculate this functional integral, I can now compute any linear observable. For example, square of the position of my particle. Is the trace of that density matrix positive? That's the question. The Krauss condition, will enforce that trace rho will remain to be 1 after averaging over this V. It's the result of the Krauss condition. And it stays non-negative. It just stays 1. Yes, it stays the proper density matrix. Actually, I have another slide which elaborates on this a little bit more. Okay, I would like to compare this with what we would have obtained if instead we were using just a random potential or random force acting on my particle. The difference between the path integral on the previous page is that I have an I now because it's a potential, and there's also a minus sign here because it's IV and minus IV representing evolution by H and by H complex conjugate. So for a conventional random force, no measurements at all, if I calculate the average density matrix, I will obtain this path integral. And what's interesting is that it's almost the same as the path integral on the previous slide. The only difference is the minus sign here. Let me go back for 1 second. So here you have a plus sign. Here you have minus sign. But this is an irrelevant constant. It doesn't do anything. Well, it ensures normalization of the density matrix, but you can always normalize it at the end of the calculation. The physics is contained within this term, and this term is the same regardless whether you have just random potential or if you have measurements. And again, the reason the sign is the same because this comes from the product I and minus I, and in the previous slide, just 1 square, both are 1. Here the sign flips because it's I square or minus I square, but it doesn't matter because it doesn't do anything, this term. So for linear observables, random measurements is the same as random Hermitian potential. And that's what I was referring to earlier, where I said that density matrix averaged over the outcomes of measurements can be also obtained by entirely unitary evolution, but governed by some random force. So that's one of my claims. And so that's the slide which elaborates a little bit more on the normalization of the density matrix. Those who are experts on Keldysh technique know that we often introduce classical and quantum coordinates, which are sums and differences of these two coordinates representing psi and psi star, of forward and backwards evolution in time. And you can actually see that the Krauss normalization condition and the trace of the density matrix is equivalent to saying that everything non-trivial here depends only on the quantum variable. It does not depend on the classical variable. Okay, so this is great, but I would now like to tell you that given this path integral, I can actually write down the Liouville equation, which is essentially a Schrodinger equation for this action, for the density matrix averaged over the outcomes of measurements, and I can calculate average position square, and now it just comes from solving this equation, which is solvable, and you'll find out that this average position square goes as time cube. Now, why is it time cube? Well, okay, so you can actually convince yourself that when you're measuring a particle, you're projecting into little intervals here and there. Every time you measure it, you give some uncertainty to its momentum, which is uncertainty to its velocity, and that means its velocity undergoes Brownian motion. And if velocity of a particle undergoes Brownian motion, square of its position goes as t cubed, because it's t integrated twice over time. So this result is not surprising, but it also comes out of this calculation. But now, of course, you could also get exactly the same result if you just apply a random force to your particle. And that's also not surprising because, I mean, maybe it's a little bit surprising, actually. But random force also gives, makes the momentum of your particle to undergo Brownian motion because time derivative of the momentum is the force. And so the square of the position is also t cubed. But mathematically, it's, of course, all follows from the fact that this equation describes both random force and random measurements. Okay, but now you could ask, what if I want to find something non-trivial about randomly measured particle, which cannot be produced by applying random force to it? And to do that, you need to look at nonlinear observables. So, and as we saw, nonlinear observables mean that you need to replicate your system and calculate observables in that replicated representation. So you replicate your system n times, create n replicas, average over your measurements, And so in case of the measurements, that's the kind of effective theory you produce. But in fact, in case of random potential, you get almost the same theory, but with minus signs in terms which couple replicas in the same Keldysh contour, forward or backward contour. Yes. Yeah.
Is this like an average of observed density, replicate density matrices weighted by one rule?
Yes. So this is average over all measurement outcomes of the density matrix.
So normally if you average with respect to one rule, you run into some normalization issues here.
Again, Krauss condition fixes all normalization issues. As long as I made sure much earlier than I have Krauss condition under control here. And so I know that this rho will be normalized.
Yeah, so the point would be that random force you get in this Caspar-Trigger equation is correlated with the wave function. And so that kind of drops out when you calculate the average single copy density matrix.
Well, but that I don't entirely understand. This is my random force, this V, random potential. It's not correlated with the state itself. I mean, it is correlated indirectly because it produces the state. But in this path integral, this is just some random variable over which I can average. And I know how to do that. It's a random Gaussian variable. The difference between measurements and force is in these I's. So non-unitary evolution, unitary evolution. Otherwise, it's almost the same thing. But it does produce, once I average, I get two different effective theories if I have replicas. And the difference is exactly in the sector, which doesn't exist when there's only one replica. You need to have more than one replica to obtain that difference.
Yeah, I mean, when you apply random force, you choose randoms. Whereas when you see that's completely random. And I agree you can have some random force, but certainly uncorrelated with the same equation. But then if I have randomness going for measurement of that, I don't choose the outcome. And that leads to another.
Well, but the outcome is also entirely random. So I can get different outcomes with different probabilities, and that's all built in here. Yes, but it's the outcome. I mean, the probabilities of outcomes of measurements are encoded in Born rules, which are already incorporated in this formalism. So the formalism knows what these probabilities are. And it so happens that for a single replica, you can replace measurements by random force. Yes, and it'll still work. Because, I mean, these are two different physical situations, but in the end of the day, they're described by the same equation or by the same path integral. But in case of measurements, you have to invoke Born rules. In case of random force, you don't invoke Born rules. You just put in random force and see what comes out. That's the claim. All right, yes, I know that I'm very low on time, so let me just say a couple of things before I finish. Okay, you can calculate nonlinear observables. For example, you can calculate this observable, which is, what is it exactly? I take a particle, I measure it, and I discover it in different positions in time, but I also allow it to fly around between measurements, just free particle. And then after some time, I find out where it is for a given sequence of measurements, and that's average x for a given sequence of measurements, and I square that, and then I average over all measurement outcomes. That's a nonlinear observable for that particle. And then the replicated theory is given by this expression instead of x1 squared here. And this can be done, and the end result is that if you calculate this observable, it actually goes linearly in time as opposed to cubic in time for linear observable. So this object here, let's see, this is right, no, it's correct, yes. But for random force, actually, this nonlinear observable coincides with linear observable, which we can discuss, but that is the property of that system. Okay, but so the end result here is that we can study nonlinear observables even for a single particle, and we can come up with this example or with this formalism of path integrals describing it, which appeals to something we learned when we first started learning about quantum mechanics. All you need to do is to put in some randomness, and it has to be non-Hermitian, but other than that, you use conventional path integrals and even Schrodinger-like equations to understand what measurements do to our system. Okay, so this said, you can now apply all of that to more complex quantum many-body systems. Now, I know that I don't have time to do this, and I don't plan to do this. I would like just to show you what you get if you start applying this to a larger liquid, which is being randomly measured at different positions. So let me see. Just want to kind of demonstrate for you the kind of path integrals you'll get. So this is a path integral for a larger liquid, which can be described by in terms of either theta or phi dual variables. As everybody here knows, K is a larger parameter, so that's the free larger liquid, but in the Keldysh form. So there's positive and negative propagating fields. And then there is these terms where rho is the density of my particles, which actually describe the outcome of measurements when I measure positions of particles, more like number of particles on given lattice sites if these are bosons. And so that is a very manageable theory, which I can study by using conventional methods of path integrals, normalization group. And so this represents some of our unpublished work. And in the end, I'll just flash this slide that by using this, you can actually uncover the phase diagram of such larger liquid as a function of a larger parameter, which is interaction strength, and measurement rate here. And these are various lines having to do with various operators in this theory being either relevant or irrelevant and driving us to different phases, similar to what David Hughes was talking about, the volume phase, area law phase. And there's one more phase, which David also studied, but hasn't told us about, the so-called charge sharp volume law phase, which can also be seen in this formalism. Okay, but let me finish by concluding that, so what follows from what I just told you. So first of all, measurements require nonlinear observables. If you study linear observables, you will not see anything new compared to what you could have discovered with just unitary evolution. You can use replicas to study these nonlinear observables. You do have functional integral description, which resembles description of systems with random forces, but deviates from it in certain places to reflect the fact that these are measurements and not just random forces, but only for nonlinear observables. And so it's definitely a new frontier of studying quantum phases. But one of my messages here is you don't need necessarily to use master equations or technique of quantum information theory to understand all these phenomena. You can just apply conventional path integrals, just suitably modified, and you should be able to uncover all these phenomena having to do with steering quantum systems with measurements. All right, thanks. I'll stop here.
I would think if you applied a lot of measurements to a larger liquid, it would just heat up to a very high temperature in some sense.
Yes.
And is that what you're finding? And once that happens, is it a larger liquid? You know, can you use the larger liquid description anymore?
Well, so what you actually find, maybe not surprisingly, that this larger liquid, once you replicate it to describe nonlinear observables, all the operators split into operators which are subject to heating and the ones which are not subject to heating. The one which are subject to heating do not depend on the number of replicas, and they survived even if you have one replica. So if you just compute linear observables, these operators will still be there. And they describe essentially random forces, because I kept talking about how measurements can be replaced by forces. You have a larger liquid which is being shaken by some forces, no measurements at all, and of course it's heating, and you can see that within this formalism. But there's also these observables which entirely decouple from it, which we can call them nonlinear observables. They describe nonlinear correlators, and those are not heating. Those have very nice correlation functions, and you can analyze them using conventional techniques of field theory that we have at our disposal. And these are replica symmetric and replica projected operators, which I think you also have. But here you just get them from larger liquid directly.
This correspondence between the measurement and the forces, so the examples that you gave had, measurements that were basically looking at the position of a particle in some sense. Is your claim that this correspondence is more general than that? Or is this, maybe specific to certain kinds of measurements?
It's a very good question. I haven't attempted to think about it in very general terms, even though I'm aware that it's a good question to ask. But I don't want to try to do too many generalizations, especially since what if it is possible to find something which doesn't fit this pattern, where you can replace measurements by random forces. But all the examples I've looked at, you can make this replacement. And it's ultimately because, well, when you look at measurements described by Krauss operators, which are close to identity, it's a simple substitution, essentially, of how you replace measurements by random forces. There is a prescription how to do this. And all the examples that I know, that prescription works. And in case of linear observables, it will not change anything. So your system will behave in exactly the same way, but no longer being measured except having random forces. So I do have a prescription, but I'm not going to claim right now that I have a theorem that it's always possible to do. But give me your favorite examples of measurements, and I'll tell you how to generate the random force. So possibly it's true.
I don't know who raised their hand first.
Okay, sorry. So the model of measurement that you're using, I guess, allows arbitrary precision in position that it's measuring, since you're the delta function. You have white noise, right?
Well, I do have white noise in time, but it's actually not necessarily white noise in space. So in space, I did not, for a single measured particle, I don't think it's actually a good idea to measure it precisely in space. Because if you locate it down to a single point, then its momentum is entirely undetermined, and it'll just fly away instantly. So I do measure it on some interval. Yeah, it was that W function which captured the interval in which I measured it.
Motion, will the results change dramatically if you couple your particle to a bath such that the motion is, viscous rather than ballistic?
It's a good question, and I think my intuition that linear observables will change, but nonlinear observables will not, because nonlinear observables, they respond specifically to measurements and not to, essentially what you're suggesting is to come up with some other channel, kind of like extra degrees of freedom with which I'm interacting and which I can act as a sink of energy, for example, so that whatever heating I'm inducing by measurements, for example, it might actually dissipate into this bath. But it sounds like that the effects of measurements in these nonlinear observables is not heating, it's something else. And maybe the bath will not really affect it, or maybe it'll affect it in some new way, but not in an obvious way. So that may be the best answer which I can give.
In the non-replicated case, is this kind of path integral the same, or at least it looks related to doing like the Keldysh for some Lindblad evolution? Is it the same or is it related?
Well, I think for the yes, so for the non-replicated theory, I think there is a one-to-one correspondence with Lindblad evolution, because you can just use those Ks to construct the Lindblad operators. And I think I know how to do this. For replicated, I think it's a little bit more complex. And I do need to look at powers of density matrices in that case.
Like if I did like maybe call this with multiple like contours or something, then it's like a different thing from that. It looks like.
Yes, would I be able to get the same? I could imagine having Keldysh with multiple contours. And I think it's actually, at least it could be made equivalent to replicated theory. What is a replicated theory? It is multiple contours in some sense. I have n fields propagating forwards and n field propagating backwards. And in the very beginning, I will tie them to the same initial density matrix. Although there are subtleties, but okay, right, we can discuss that later.
Way to write the same function or using different alpha, which is a sort of a general thing like it.
Okay, so there is a general way to map that into forces.
And amid infinitely many rewriting using different crowd but only when you care about
But I think it's crucial that I'd like to replace Krauss operators by unitary evolution operators, right? Okay. All right.
All right, with that, let's thank Victor one more time.